manipulation of the field. So stretch a bit, and that'll be quite fast. But please interrupt me if you're missing something, if I'm going too fast. But let's begin with the idea that we had a box, we had boundaries, we have quantized it, we have the modes determined by wave vectors associated to angular frequencies and polarizations. Field will be our observable, and the electric field can be decomposed in two parts that will be associated with the creation and annihilation operators, or can be associated to x and y quadratures of the field. And here we have the definition of them in terms of creation and annihilation operators. That said, let's step back and see, okay, now this very crude drawing, what happens when you add some spice on this Hamiltonian. We're saying that we have an interaction Hamiltonian affecting our cavity. So we have a resonator. Instead of the box, I will play with two concave mirrors that will define a space profile that will result in something that if you pump, there'll be a leak, and you have a profile like this dot of the laser, something that looks like a Gaussian in the intensity distribution. Okay? That's just classical optics. The empty box will be something like this. We are looking at just one mode of this resonator, a Fabry-Perot resonator, or we can look at a set of different resonances here. Please take a look in Walls and Drummond, chapter 5, to follow it. But the idea is that now we have the interaction, and can be different effects. I can send an intense beam here, it will leak into the cavity and act as a driving field. I can take an antenna, get close to it, irradiate power, and some power will leak inside of these mirrors. In this case, superconducting mirrors, as in the case of Serge Laroche experiments. Or I can have also a nonlinear medium inside. A crystal, atoms, whatever, not vacuum, that will be coupling the different modes that you have here. When I say nonlinear medium, I'm saying something that's, okay, once again, classical electromagnetic theory. So we have a displacement operator that's proportional to your to the electrical field. That you add the polarization and the electric field, giving the resulting displacement operator. But if the field is strong enough, this susceptibility will be described by an expansion of a series involving higher order terms. Second order, third order, so on and so forth. So, if you look at just the second order term, you have the field square that will lead to a series of terms. There's a whole course on nonlinear optics that you can play with. But each term here can be associated with a different characteristics. Say you send two fields, E1 and E2 at frequencies omega 1 and omega 2. When you square it, you have the double of the frequency of one field, double of the frequency of the other. That's called the second harmonic generation. You can have the difference of their frequencies appearing. You can have the sum of their frequencies appearing. You can have even a DC that will appear, something known as optical rectification. So all this only in the second order. If you go to third order, you have a nonlinear refractive index, four-wave mixing, Raman scattering, so on and so forth. But that will be a tool because it's coupling different fields inside your Hamiltonian. So this term here will be involving all these kind of creatures. Eventually, atoms coupling and sending light into and out of the field, exchanging light here. That said, Let's begin with the simplest case. The simplest case would be taking those mirrors and putting them away. We extend it, and we can consider only an incoming field having the interaction Hamiltonian at a specific mode, therefore a specific frequency, and having a field in the output that's processed by this interaction Hamiltonian in free propagation inside our medium. So the Hamiltonian for a single mode would be something like this. The evolution can be described here using Schrödinger representation. So the evolution of the state will be a unitary operator acting on our initial state. So if you solve this equation for the evolution, what you get is this transformation that involves the exponential of our Hamiltonian. So nice to take a review on Schrödinger and Heisenberg pictures on quantum energy. So you can see the operator in the Schrödinger representation as expectance value under the evolution of the fields, or the unitary transformation here involving here your operator. That can lead, therefore, to the Heisenberg picture. You can put the evolution into the operator as well, and then check the evolution of the operator in time, following a commutation relation involving the operator and the Hamiltonian, leading to an equation like this, and this contribution in the Heisenberg picture involving the natural evolution of the operator that can be suffering some other evolution that are not related to the state evolution. So you either can evolve the state, evolve the operator, or sit in the middle. You let the states evolve with the free Hamiltonian, so that you take the fast part of the evolution, the rotating part, and then you look at the evolution involving only the interaction operator. So this one will be describing the evolution of the operator, and this one you use to evolve the state. That's fine? Separate both parts, so things becomes easier, equations become simpler. So the state of the field evolves here, and here we have the evolution under the Hamiltonian, the interaction Hamiltonian. When you go now to the evolution, what you get here is you separate this part, the fast part, and let's see what happens now with different situations, like the driving field. What's a driving field? It's something that enters in the field, and we coupling creation and annihilation operators with a certain rate. This rate will depend on this constant. So now, in the interaction picture, if you look at the evolution of your operator, it will evolve like this, and after some time, what you get is your initial operator plus a constant. That, in fact, will be the generator of a coherent state in this process. And the mean field will be given by this term. Basically, the coupling rate multiplied by the time you're acting on it. That's a way of seeing what's going on in a cavity and insert some light into it. So you take the vacuum and displace it. That's the idea, that's the operation, that's the result. But now let's see something involving those nonlinearities. You can understand those Hamiltonians of the coupling as the combination of three field operators, the annihilation of a photon in a pump field, and the creation of a pair of photons in two modes with frequencies smaller than the pump frequency, but they add up in frequency. Omega 0, omega naught is equal to the sum of omega 1 plus omega 2. Or you can have process like the 4-wave mixing process. Okay, you say 4, but you see 3 fields here. You're taking 2 photons of your pump to produce a pair of photons in the converted fields. That's one example. Those are 2 examples that leads to amplification. That's called the parametric amplifier when you have a strong driving field. And that's the tool that we'll be looking here. First, in simplest case, the degenerate one. So both fields are produced at half of your driving frequency, we'll call it 2 omega. That's the inverse process of the second harmonic generation, where you take 2 reds and produce 1 ultraviolet photon. Here you can take an ultraviolet photon and produce a pair of red photons at the same frequency. They're degenerate, so you have A dagger square minus A square. So that comes from the inharmonicity of your oscillator. That displacement operator with that expansion comes from the fact that, okay, just the linear term is that your electron is bounded and you describe the restoring force of your electron to your atom by a linear response of the field, of the medium. So it's a quadratic potential. But any distortion on this quadratic potential will lead to those higher order terms. So that's the inharmonicity of your harmonic oscillator that you're driving with light. Now, that's your interaction Hamiltonian. And when you make the evolution of the operator, you look at the commutator here, when you do the calculation, you see that the evolution of A is coupled to the value of A dagger. And vice versa. The evolution of A dagger is coupled to the evolution of, coupled to the value of A. To do this calculation, just put the commutation relations, do that at home, take your time, and see that the solution here will be an amplification process, and at the end, you have a field produced in the output where you take the evolution of your initial state plus the Hermitian conjugate, involving here a exponential evolution. And now comes the part where you see the amplification. Let's change it a little bit. Let's look at the quadratures, combining symmetric and non-symmetrically creation and annihilation operators. When you do that, you have a quadrature of the field that will be amplified. It's multiplied in the evolution of time, and the other one is de-amplified. Remember, it's not attenuated. You're not throwing anything away. You're reducing it. You're squeezing. That's different from attenuation, as you're going to see tomorrow. Attenuation is that you get a light field, put a beam splitter, throw away some parts in the garbage, and detect only a fraction. So you're coupling your system to another one. You call that a reservoir. At the end of evolution, you see that you have amplification of one quadrature and compression of the other. That's exactly what a squeezer does. It takes it, squeezes, and variances. We will give a product that still saturates the uncertainty relation. Afterwards, if we want, you can displace it, but that's not necessary. You can stay only with the squeezed vacuum. That's fine? Following me? Okay, now let's make it with 2 fields. The amplification process, you have the 2 modes and your Hamiltonian, okay? The pump here, I'm treating it just as a classical field. It's the driving field that's feeding energy into the converted modes. I don't look at it at quantum level, so I put the driving field here on my key term. That involves everything, morphology, crystallography, orientations, nonlinear response, and the driving field. Just a coupling constant. Now what you have is either I create a pair of photons or I annihilate a pair of photons. The pair of photons add up to the energy of a single photon of the pump. If I do again the calculation, I see that the amplification process now will couple one field to the conjugate of the other, and vice versa. Solution again will involve an exponential growth along the median. But it's nice that this equation can be decoupled. If I make this substitution, I go to a sum space where I look at the sum of the two modes, and a subtraction space where I look at the difference of two modes. I have a question way back. Maybe we can, maybe for the people on the network or for registering, just.
Testing, thank you. Professor, I'm not understand a point because by your equations, you have an exponential gain to your quadratus, but how can, but it will saturate by conservation of energy. Yeah. So how I can include this in my equations?
That will come soon.
Okay.
For the moment, is what we are calling the undepleted approximation. I'm entering with something like 10 to the 14 photons per second, and in the output, I'll have some hundreds of photons in the down-converted mode. Okay. In that case, it's pretty immediate, so you don't deplete your pump, and you can neglect the effect of this conversion. But consequences will follow when we take the three fields together. And now, instead of having only two fields that are affected, you can have 3 or 4 fields or more. So that's a nice toolbox that we'll get into in a few. Thanks for the question.
Okay, thank you.
For the moment, we're just changing the referential. It's like having 2 oscillators, and then you look at the center of mass of the oscillator, and for the relative displacement of these 2 coupled oscillators. Fine? So when you make this change of referential here, but that interaction Hamiltonian, you see that you come with 2 separate parts. One Hamiltonian for the squeezing, for the sum mode, and a Hamiltonian for the squeezing in the subtraction mode with a pi phase shift. Consequence, it acts as two squeezed states. One squeezing sum, and another one squeezing subtraction. That's pretty nice. There's a nice consequence that comes out. If you look at the Wigner function here, involving sum and subtraction, when you go through the calculations of this state, okay, first you have something that's a Gaussian, you process, you squeeze, you stretch, you end up with a Gaussian like this. But in fact, a product of 2 Gaussians, one for the field in the mode plus, the other one for the field in mode minus. We can rewrite this. We can have an arbitrary displacement, can bring this down to 0, if you wish. Just you enter vacuum, you get the mean value still equals to 0. And when you look here, you see that you have squeezing in the difference of the x quadratures and in the sum of the y quadratures for r smaller than 1. So that's the situation where you see squeezing in these 2 quadratures, and that has a name. Who will guess? It's not squeezing? What's that? That we called entanglement. Okay? Let's take a look in this 2-mode squeezed state. That's another name of this creature. It's a 2-mode squeezed state because they're squeezing the mode plus and mode minus. If you take the partial trace here over 1 dimension, what you have is the Wigner function for only one of the fields, say field 1 signal. when you look at this field, what you have is a Gaussian, but with a width that will grow up with the squeezing that you put into it. Remember, if you have vacuum, you have a certain distribution of your Wigner, a certain distribution in your quasi-probability function. When you have a thermal state, that will grow up, that will become broader. And that's what you have here. You have a broader distribution of possibilities of measuring your state. It gets wider, it gets noisier, it is a thermal state. So you amplify, you get a thermal state in one side, it's symmetric, you have a thermal state in the other side, so you have lost information on each side. You had pure states at the beginning, you end with excess noise, you lost information locally. Yet, the process is unitary. You begin with a Hamiltonian, you evolve it, you can make the film move backwards. You can re-inject those fields back in the crystal and get it back to your initial state. So you're not losing information. You're losing information locally. That means that you gained shared information. Another interesting way of looking at it is in terms of number of photons. So let's see those states in the number state description. When you take this evolution in the number state description, you have the application, successive application of creation and annihilation operators. At the end of the day, what you have is this function here, that's just the thermal distribution that we had before, involving n modes in being 1, n photons in being 1, and n photons in being 2. You have perfect photon correlation, but a thermal state on each side. If you take the partial trace in one of the modes, what you get at the end will be, remember that n average, the average number of photons, here will be something like a hyperbolic sine of xt, or something like this. So we can rewrite this as a thermal state if you trace the other mode. Here, described in the number of photons. Are you okay now? Finally up to the moment. You have perfect photon correlation. If you have just a single mode, remember, the squeeze state will produce pairs of photons. To have perfect, for a single mode, a degenerate parametric amplifier, you produce pairs of photons that leads to squeezing. For a non-degenerate amplifier, you produce pairs of photons in distinct modes, and then you have perfect correlation in the number of photons. That's what we call a signature of entanglement. You have seen a bit of entanglement along the last few weeks, don't you? Who have never heard of entanglement in this room? Okay, so I'll go really fast for the next pictures. That's the origin of entanglement comes back from 35. And I said that most of the quantum mechanics, or practically all of that, was written by this time. Okay, you had it written, but you still was fighting to understand. I strongly recommending you to read this article, because it's really complicated to define and translate what they are saying with what we use. Say that they propose a state where you produce a pair of particles that are in a strongly correlated state in the difference of position and sum of momentum. So that's the Wigner function. It's a nice way to write this situation. And as a consequence, okay, basically what you have is that a measurement in position here gives you the position of the second particle. A measurement of momentum here gives you the momentum of the second particle. But wait, this particle cannot be in an eigenstate of position and momentum. Quantum mechanics forbids it. Schrödinger, the uncertainty principle forbids. You cannot measure this particle and affect the second particle. That would be superluminal contact. It's not something like this. So there's a mystery, and there are propositions that there's something missing, maybe the instructions of whether it's X or the values of X and P are written here somewhere else that's not clear on this function, so the quantum mechanics is not complete. There should be something missing in the back, and a more complete theory should be available. And Bohr says that, okay, there's complementarity, there's this nice footnote where it shows that you have a combination, a change in your referential that leads to two observables that are perfectly commuting. This Q in the mode of the sum and this P in the subtraction of the modes, in the mode of the subtractions, that are perfectly commuting, so you can measure exactly this observable here and this observable here. You can have both with the highest degree of precision at a cost. If you make a measurement, you have a completely random output in one site, a completely random output on the second site, but they are perfectly correlated. Fine with that? Okay, that's the idea that strong entanglement comes at a cost for local information, but global information is maximally kept. So we have a limitation, although we have a limitation for information in the quantum mode. You cannot produce a particle simultaneously in eigenstate of position and momentum. You can have, on the other hand, extreme non-local correlations, perfect non-local correlations, as would be in a classical world. So some ways to detect entanglement. One of them, proposed by Margaret Reed and Peter Drummond, is called the EPR criterion. So you have one mode here. You make a measurement of mode B, and upon the results here, you can act on the first mode to get the best estimate possible of a certain observable here. So with this processing here, when you make the calculations to optimize that, you can get what is called the inferred variance. You can get a reduction of the noise here by compensating with the correlations. You can make, for instance, a variable beam splitter here, giving you some attenuation. Making the calculations, that's the inferred variance, and they say that you have entanglement, EPR type, if this inequality is violated. So when you have an apparent squeezing on both inferred P and Q quadratures in one mode, then you have entanglement. Okay, you're not violating the uncertainty principle, you're just trying to see if upon the measurement here, you can reduce the noise here and compensate for that. That's one of the tests. Another one, go back to those variables, combining X and P quadratures on both sides. That's the Duan, Gidg, Sirac, and Zoller criterion that looks at a linear combination of Q and P quadratures on both sides. And whenever you have the combination of these two beating this limit, you have a signature of two entangled states. Otherwise, separable states will give a value greater than 2 for A equal to 1/2. Square root A equal to 1 here. What's called a separable state? I say it as it's called separable if you can write the density operator as a convex sum of states, and those states are just a tensor product of state 1 and state 2. That's the definition of a separable state. If your state cannot be written like this, then it's entangled. The point is, if you see this, it's hard to say what would be the combination of possible products that you can take here on the other side and their weights. you can see by tomography only this term here. But then you can play some tests. EPR, read Drummond EPR is one test. This is another test. And basically comes to a nice site. Okay, just I'll skip this a little bit for the moment. No, we're going through that, okay? Just to make a disclaimer here. Sorry about that. There's a common feature on all the states that I have presented you now in this section. We had squeezed, we had thermal, we had coherent states, we had vacuum. All of them are Gaussian. So what do you need to characterize a Gaussian? The mean value of the Gaussian, that's just a displacement, a change in your referential, no quantum feature on top of that, and the width of the Gaussian, the variance. So these are the only two terms that you need to describe a Gaussian. So if the state is Gaussian, a good mapping of the density operator of it, or the Wigner function, or the P function, or whatsoever, is the covariance of the state. What I'm writing here is the covariance of a two-mode system, where you see here the variance of P and Q for the first mode, P and Q for the second mode, the correlation between P and Q for the first mode and second mode, and the cross-correlation between these two modes here in this off-diagonal matrix. And that's something that you measure in the lab, using the techniques that we have seen in the morning. So you can make the tomography by measuring it and checking out, is it compatible with a Gaussian? If yes, then this is equivalent to the density operator. Okay? So, what does it mean to make the Duan, Gibbs, Rack, and Zoller tests? It means that you can take two states that are thermal, combine them on a beam splitter, and check out in the output if you get squeezing. Okay? I'll tell you that you have done this before. Remember when I mentioned you that V plus and V minus operators for the two modes squeezed state? You have two squeezing, a linear combination, and then you have in the output two thermal states. You're just changing the basis. So with two squeezed states, you can produce a pair of entangled modes. In fact, with just one squeezed state, you can produce entangled modes. I have a question from the audience way back.
Hi, Professor. About this one that you show us, my question is about, it's equivalent to say that we can basically sum these states and apply like a block rotation, like the superposition of the states, and apply like a rotation in the block sphere, and basically it's kind of rotation, and then you basically have the superposition states, but of course doing this rotation in the block representation.
It's, I think that here would be a little bit tricky for making that mapping that you're proposing, okay? Because in the block sphere, okay, you have two orientations, and they can be associated to measurements, say, of your spin, of your of the state, or a two-level state. Here, I'm making a 2D mapping of your problem. Okay, in fact, there will be a 4D mapping of the problem involving either two maps that get correlations between each other,
okay,
or if you change the basis, one map and another one that don't share information.
Okay.
So you have just a product of two separable maps, 2 times 2D maps. Okay? So I don't see much how to transpose that into the language of block sphere.
Okay.
Okay? But it's more that change in the referential. And that's a way that can either see how to generate entangled states, you can take two squeezed states, and send to a beam splitter, or you can take, or you can take the generation or the parametric amplification and produce directly two thermal states that share correlations.
Okay.
Okay?
Thank you.
So basically, another question here.
Yeah, thanks. Does this have to do with the Hangul-Mandel effect?
Because
of the squeezing?
Not directly.
Not directly, but yeah, you have like a pair numbers of photons for the squeezed states.
If you go down to photons and begin to look at the Hangul-Mandel,
Yeah.
the Hangul-Mandel effect is the case where you play with just a pair of photons.
Yeah, totally.
One photon in one port and the other photon in the other port.
Exactly.
So that can be seen as an extreme, the Hangul-Mandel case is an extreme situation of this combination here.
Okay, thank you.
That will be subject tomorrow. There you see two machines that can build with the Hangul-Mandel.
Okay.
More questions? So you see that when you get this process and you get squeezing, then you have a signature of entanglement. That's the opposite of that proposal for entanglement generation. Get two squeezers, mix. You begin with two pure states and end up with two mixed states. You have degradation of information here, you have excess of noise, but you have correlations at quantum level between both sides. Sharing of information. Fine? Question?
I don't get, how do you do this in the lab? How do you make this interaction, these two?
You send the two beams inside in a glass plate.
So you send the...
Just that. That's why I
really?
said that
So-
the beam splitter is a powerful quantum machine.
So you send two beams in a squeezed state and put them to interact through okay, nice.
In the glass plate, and then what you have in the output, if you measure, you have thermal and thermal.
Cool.
Okay, you have to be careful with the phases. Okay, so you'll be combining them with the orthogonal quadratures. Otherwise, you can combine them with the same quadratures, and the output will be something different. So you have to carefully adjust the path between both sides, just as we do with an interferometer.
Thank you.
One question right behind.
And it requires no nonlinearity or whatsoever.
Sorry?
It requires no nonlinearity. Nonlinearity.
The nonlinearity is in the production of those states.
Okay.
Afterwards, it's just the dynamics of the beam splitter itself,
Okay.
coupling that pair of modes,
Yeah, thank you.
making that linear combination of the modes at the input.
Yeah, Professor. When you model this kind of interaction, you use a specific kind of interaction Hamiltonian, and is mixing two modes of the harmonic oscillator. But if you try to solve the complete problem of two oscillators that are coupled, there are more terms in the interaction. So I like to know if there is other kind of interactions that you can consider in order to have more information about the interaction of the two modes inside the nonlinear medium.
Here in this process, we have the two oscillators. In fact, it's really a pair of coupled oscillators that you're dealing. In this description, using only the Chi2, what you have is you can really take the solution, separating the fast part in the evolution of your state, so that's the basis that you're looking at, and the evolution of the operators will give you the complete outcome. So that's really the final solution. It transforms whenever your Hamiltonian has only bilinear terms, and you do that commutation, you end up only with the linear evolutions of your operators when you make that commutator.
Okay.
And that's nice. You'll be doing squeezing, you can do losses, or you can send two fields and couple them, transforming it in another pair of fields. But yet, as far as it's bilinear, you take Gaussian, you end Gaussian. And you don't distort anything. But if you add anything beyond first and second order terms in your Hamiltonian, now you have distortion. Now it won't evolve only as a Gaussian, but you can distort the Gaussian, you can even stretch that, make a circle. But that would be a very extreme case.
Okay. Thank you.
That's fine? Okay. So that's the way we generate entanglement. But yet, there's something that I call the best test possible, and is of an ingenuity absurdly ingenious. It's fantastic how clever it is. It was proposed by Asher Perez and the Horodesky family, I may say, 3 or 4 of the Horodesky that proposed this way of separability criterion for density matrices. In this case, they're operating with 2 matrices. They are involving qubits in one side and the other, so 2-level systems. So you say that you have a matrix that's written like that. That's the definition of a separable state. If you make a partial transposition, okay, if you take a density operator, a matrix, and you transpose that, that's the equivalent of reversing the evolution in time, for instance. No problem. Okay, just moving the film backwards, everything is unitary. If you take the density matrix and transpose it, that remains a valid density matrix. It's completely positive, has no negative eigenvalues. It's a valid physical state. If you'd take this, and if you knew what are those operators here, the local density operators, you can transpose them and yet get a physical state. But this is not physical. You're not time reversing it, the evolution of your state. You're just making a mathematical operation in one of the subsystems. Okay? Now's the tricky part. Making the transposition is just shuffling around the terms in the off-diagonal terms of your density matrix. When you do that, just shuffle it, going from a matrix like this to this, okay, or not, you don't need to know what are these inner matrices. You can just make this operation by exchanging terms, and then you check out for the positivity of this outcome. If the outcome is non-positive, then this matrix is non-physical. Therefore, you cannot write this matrix like this. Therefore, it's unseparable or entangled. Okay? You just make the tomography, make this operation of exchanging some of the terms in the off-diagonal, and see if the matrix remains physical. If not, okay, so we cannot write like it like this. This nice proposal for Asher Perez for qubits can be extended into the continuous variables. And what's nice here, if you're playing with the Gaussians, is a unitary map from 1 to 1. You have that 4x4 matrix. You go to a 4x4 matrix involving the variances of the field. And here, Simon made this treatment, so you can write now your physicality of the matrix can be seen as the positivity of this combination here, your variance matrix plus I over 2, this symplectic matrix. What's a symplectic matrix? It's a matrix where you can make rotations or squeezing, and it doesn't change its form. That's exactly making local operations. The local operations are not changing the nature of the matrix. There's a whole lot of calculations there. For an experimentalist like me, it took some time to digest it, and lots of simulations or checking it out in MATLAB or Mathematica, or take your program of preference, Python. But what's nice here is that this time reversal here is equivalent to take your Wigner function, and then you flip one of the quadratures, one and only one of the quadratures. So that's equivalent of a partial transposition, and this new Wigner function associated with a new covariance matrix can make again the test of physicality. And if the resulting matrix is not physical, then the state is entangled. Basically, you diagonalize it, check for the eigenvalues, and if one of the eigenvalues is smaller than 1, you have a violation of the uncertainty principle. Okay, it violates because the transposition, partial transposition here, does not return a physical matrix. It's the transposition of the Peres-Hordesky separability criterion in continuous variables. Fine? What you do is just take your matrix and multiply line and column by -1, and check out if this is a physical matrix. It's equivalent of taking our states, flip here the sign. You don't buy that from Tor Labs, Coherent, Melgrio, or whatsoever. You're not going to find that on the catalog. That's just a mathematical operation with no physical equivalency. You would send that into a beam splitter, and what you have in the output is a noisy state, and boom, borrowing boom from Olivier Pfister, you have a state that violates the Heisenberg uncertainty. Okay, it violates because you cannot make this transposition here and remains with a physical state if the states are entangled. In that case, it's if and only if. If the state is not Gaussian, eventually you cannot detect entanglements by this, and you need to recur to other techniques. But if it's Gaussian, that's necessary and sufficient. Okay? Fine with that? Okay, you can go further and look for tripartite entanglement, stand GCZ for 3 or 4 and more variables, or can apply PPT when you have multiple partitions. You can just take your 3, 4, 5 systems and look at all possible ways that you can decouple these n modes into bipartitions and apply the tests. Whenever you have a violation, you have a signature of entanglement. Fine with that? Okay. We're going to get back to those measures. That's just an explanation of how you measure entanglement in continuous variables domain. One last word for the process that I've described to you. This parametric process often is too weak. You get a very faint field coming out, a small squeezing. Lately, you have developed higher gains, long fibers, so you extend the interaction, and you can have a significant gain. You have new materials where you can use strong pump and get, once again, a good gain. or playing with atoms. Close resonance, not so close so you have absorption, but close enough to have a strong nonlinearity. Or you can take a weak nonlinearity and enhance the effect. How you do that? You send light over and over and over and over it. But your process inside a cavity. And some curious effects will appear. You have basically the coupling of your cavity mode with all the modes here involved, and you have to treat the rest of the universe as a reservoir where you're exchanging energy with it. There's a specific formalism that's a bit different from what we have seen with a single pass in your amplifier. But in fact, you can consider that as a combination. You have, say, 3 modes. They are spatially overlapped using the same mirrors. And then you have a nonlinear process that will be coupling the 3 of them. And now, in this Hamiltonian, you can reach situations where you have to consider the driving field. And you cannot take that any longer as a classical parameter. You have to look at that quantically. And you see now, you have a 3-linear Hamiltonian. Depending on the situation, it can be non-Gaussian. That's what you call the optical parametric oscillator. You take your parametric amplifier, your optical parametric amplifier, but feedback, it becomes an oscillator, just like a laser. Your pump field will have annihilation of photons, creation of photon pairs that will leak out of the cavity in pairs. So whenever you count one photon, the other one should be coming around nearly. And you'll be depleting the pump in a quite controlled way. It's not that you have just a random depletion, but you have you affect the pump. So with this machine, when you work below threshold, you have strong squeezed vacuum. Or you can have entangled fields if you are not degenerate. Or if you are above threshold, you have intense entangled fields. You can have squeezing of the pump. You can have squeezing in signal and idler. You can have entanglement between signal, idler, and pump. You can have 3 entangled fields, each one at a different wavelength.
I have a question.
Sure.
What is this threshold regime?
The audio system here is pretty good, so I'm not able to reproduce a microphony. Whenever you have a process, you have the gain inside the cavity, and then you have a loss rate. If your gain is smaller than your loss rate, you're just sending photons into the cavity, it's leaking out, and then you don't have an active feedback that will build up. Whenever your gain match the losses, the feedback will lead to an amplification, and then it begins to build up. And then you have that exponential growth that your colleague mentioned. But since you have an exponential growth, it should saturate at some point. You begin to drive away energy from your driving field, and then the driving field will be depleted. That's the threshold regime. You're actively taking energy of the pump at a strong rate. The pump will be clipped at a certain value, and if you double the input pump power, the intracavity power remains the same. The excess that you're putting here will be dropped away on this side, and you have a pair of laser beams coming out. So that's the difference between subthreshold and above threshold. When you are subthreshold, you don't have significant pump depletion. Okay, if you go to the details, eventually you may see some signature. But it's very, very faint. Now you need to take care with your expansion when you go to the cavity and you look at it on that triply linear Hamiltonian. So you can linearize that and take the mean fields under this linearization, or in that case, everything will be Gaussian. But if you look exactly at the third order term, you should go away from the Gaussianity. Now the trick is how to make that run experimentally. Computer can accept being at less than 1% at 0.1% above or below the oscillation threshold, but you're never going to be at a stable situation 0.1 or 0.1% above or below threshold. Everything in the lab shakes, including the laser, okay? So don't expect to be that sensitive. Nevertheless, you can make new machines like those that you have seen in the lab, the OPO with the rubidium atoms, that they can extend this range of the threshold to some tens of %. Now, we are talking about business. We can lock the laser as stable as that. Okay?
Thanks.
So, what are the states that we are producing? The output will be something like this. Almost thermal. It's not exactly thermal because it can have one quadrature with less noise than the other. That's what's called squeezed thermal state. But it's not squeezed in terms that you get below the uncertainty of the coherent state. So it's just your ellipsis of thermal state with some squeezing in one direction, but everything with excess noise. And when you combine it, for the difference between signal and idler, you can see correlations in intensity. When you look at the sum, you see correlation in the phase. Where does that come from? Energy conservation. Intensity is related to photon number. If I produce photons in pair, I can have fluctuation in photons, but they will be correlated. Phase is related to energy conservation. So you have the angular velocity here. If one goes up a little bit, the other one should go down a little bit, so they keep with the pump. So they'll be doing like this. They're correlated in this orientation and anti-correlated in this orientation. Okay? That's the picture that you get in the output. But how to make the calculations? Often, you just make the use of a master equation. You have the evolution of your system coupled to a reservoir here. When you make the calculation of all the rest of the universe as a Markovian reservoir, you are going to have those relations involving the damping of the cavity. You can, from that, make a substitution. That's something that I have evaded along, but it only comes here. When you have the density operator, you can rewrite that as a quasi-probability representation, and then this equation will be translated into an evolution in time, and all these operators will be related to derivatives on the quadratures. Now we have a differential equation that if you have only derivatives up to the second order, that comes from the bilinear response, that can be translated by a Fokker-Planck equation. Therefore, you have an equivalent Langevin equation. The evolution time of your fields, you have a drag term and a dispersion term involving a fluctuation, a Langevin fluctuation. If you're using the Wigner representation, now it's nice. The sense of this Langevin fluctuation are the vacuum fluctuations entering in your cavity. That's another reason why Wigner functions are so popular. You can have a direct interpretation of it. What does it mean? Fine? Questions here in front. Microphone on this side. Going down the way. The battery is gone. Can you hear me, Major Tom? Your circuit's dead.
Sorry, forget the question. Can you go back to the previous slide, please? It's not that clear for me how you can represent the irreversibility of the Limlat equation using a Fokker-Planck equation. No, because in the Fokker-Planck equation, how do you put the losses terms from the above equation in this Fokker-Planck equation where the terms are?
Every term here, every operator of creation and annihilation will be related to either C-value numbers or derivatives of C-value numbers. And you have a certain ordering of substitution here of these operations. Both here, those are written in terms of creation and annihilation operators. So all these operators will be acting here and changing into those derivatives. So, consequences? These lost terms will give contributions in first and second order. Contributions in first order will be related to the damping. Say, you put light into it, and then energy goes out. But also, they becomes in terms of this term that gives diffusion. Now, it's nice that be related to that dispersion diffusion theorem or diffusion
Fluctuation dissipation relation.
Exactly, fluctuation dissipation theorem. So whenever you have a fluctuation that involves also a dissipation, so the damping of the cavity will be related to those fluctuations that are entering the cavity, and that will be written here on the ways that you have on the derivatives. So here we have a gamma appearing here, and we will have a square root of gamma appearing here, keeping the fluctuation dissipation theory. And that becomes wonderful when you go here and linearize and put that in the OPO. As a consequence, when you look at evolution, you have, for one quadrature, say, difference on the amplitudes, it gets an over-damped process. Consequence of the over-damped, you squeeze it. But that always comes at a cost. If you squeeze, you should have excess noise on the other side. The excess noise comes in the difference of phases, the conjugate. If one can be perfectly squeezed, the other one should diffuse completely, and that's what happens. You have strong diffusion of signal in either phase. They just walk randomly without any bound. You have only fluctuation, no dissipation. Thanks. So, with this idea, you can just make all the calculations, make these correlations, and now move to the frequency domain. That's often where we measure. We are always measuring in the frequency domain using a spectral analyzer or a demodulator to get rid of excess noise. Okay, just multiplication of matrices, and then you end up with a covariance matrix. In fact, often a spectral matrix that can eventually relate to this two-time correlation matrix that you never measure. I hadn't seen a single measurement on this domain, but lots of on this domain. Okay? Let's move on. So we have 3 modes involved. You can discard those correlations between phase if you lock correctly your OPO, you stabilize it. And now, looking at the correlations, if you go to the sum and subtraction, what you have here is a nice map where you can see here twin beams above threshold, squeezed vacuum below threshold. The combination of these two, you have squeezing on this quadrature and on this quadrature. That's exactly that two-mode squeeze state that we have mentioned before. So you have entanglement. And you can have squeezing of the pump. And you have correlation between pump and the sum of the modes that leads to tripartite entanglement. Okay, now the funny part. How do you measure that? First, making squeezing, as was done by Jeff Kimball. Remember Kimball from the Dagenet and Mandel experiment of the supersonic light? Now he's leader of group and is making these things run. So he's taking here a neodymium egg laser, doubling it, sending the green light here in the optical parametric oscillator. You have the nonlinear crystal that's kept in a resonance at 1.06 micron that will be producing here a mode in the vacuum. And the laser here serves as a reference, your local oscillator. So what you have here is a field with zero mean, okay? The field has zero mean, but you have energy there, it's fluctuating. When you measure the fluctuation here and you move the local oscillator, you see that the noise comes down and up as you move this. And this you're ramping up. Okay, this feature is just that you're ramping down quite fast, so you have all those oscillations, and then again. Okay? What you see then is squeezing. But how do you know that you have a squeezed state? Well, you just block the light here and measure this level of noise. So you have a reduction to something like 70% of the vacuum noise. That's the squeezing. That's the first measurement. Questions here? That will be repeated over and over again through history to the extreme point of getting, instead of, say, 2 dBs of squeezing, 20 dBs of squeezing for LIGO, for you to measure gravitational waves. That's the zoom of the squeezing area. There's this nice experiment also run by Claude Fabre in the following year that takes the OPO, pump here with an argon laser, and send it in a beam splitter. But this is a polarizing beam splitter. In this process, the pair of photons are created in orthogonal polarizations. Now you can tell them apart. The other one, they're created in the same polarization at the same frequency. So they're degenerate. Here, they're non-degenerate. They're in orthogonal polarization, and with a polarizer, you send one to one side, the other one to the other. In fact, they're not even of the same frequency. They can be some few nanometers apart. You don't care. You just count how many photons you have here, how many photons you have here, make a subtraction, and check it out. Sorry. Check it out. That's below the shot noise level. How do you measure shot noise level? You rotate this half wave plate. Now, the signal mode is rotated by 45 degrees and separate half in one side, half in the other side. Either mode rotated by 45 degrees, half in one side, half on the other. As I mentioned, they're of different frequency, very different frequencies. So you're not seeing the bit note. It's very high, very far in frequency. You're averaging it. So you're just adding the number of photons. It's like having 2 beam splitters acting that will be returning your quantum level of reference. Okay? Questions? Next step. Check out for the pump. You just take your light here, get the light amplitude and phase, quantum correlations. Whoops. Okay, that's just a comparison once again. Another level of squeezing. Let's go to this just to show that you can get more squeezing from this correlation of the beams. It can get you 10 dBs, reduced by tenfold the noise. And now, when you go to non-degenerate parametric oscillators, you expect here to have correlation like this for the difference of amplitudes and sum of the phases. You can also have squeezing from the pump. Okay, it's quite blurred, but you have a reflection of the pump here, and then you measure here, and you see some squeezing coming out. Going a little bit faster, and going now to something more relevant. That's the Einstein-Podolsky Rosen generation. Once again, Jeff Kimball here on Caltech. So what you have here is a KTP crystal producing a pair of modes. You send into arms and make a measurement with local oscillators. And you compare the quadratures on both sides, measuring the inferred variances. So you see squeezing for every combination when you make the combination of X and X, Y and Y. So that's the signature of entanglement when you're working below the threshold. So you can see here two thermal states that are quantum correlated. Or going above threshold, that's what we have done in 2005. That was the work of thesis of Alessandro Villar. He took the light coming out of the OPO to 1 milliwatt beams coming out and used the analysis cavity to rotate the noise ellipses. So here you have the sum and subtraction. Far from resonance, you're measuring amplitude. Amplitude is correlated. So you can see squeezing on the difference. And when you go, as you scan, close to the sideband here, the difference gives excess noise, and the sum now gives you squeezing. So you can see that you have squeezing in the sum of the phases, squeezing in the difference of the amplitudes, so you're violating Duan inequality here. So you have entanglement. Things can be even further complicated. You can have 6 entangled modes if you look into the details of the sidebands. So if you look at it and take the Hamiltonian and look in the details of those sidebands, either plus or minus omega of the carrier frequencies, that's the nice part, that trilinear Hamiltonian becomes a set of bilinear terms and a trilinear term that has no driving field. What makes this term dominant is this driving field that is strong. The trilinear term can be neglected here when you are above threshold. And now what you have is 6 modes, here upper and lower sideband of signal, upper and lower sideband of idler, upper and lower sideband of the pump. They're quantum correlated, but, now there's always a but on this, the history. They're coupled to a thermal reservoir. When you have this strong field inside the crystal, the modulation that you have in the refractive index due to thermal fluctuations, so you have a fluctuation in density due to the phonons occurring inside, it will be shaking it like this. It's equivalent to have a phase disturbance on your field. You have an excess noise. You're scattering light of your carrier into the sidebands. And that's the damaging part of this process. You have to cool down the crystal a bit to reduce this noise as far as possible. But the fact that now you can take an exploration for all the 6 possible correlations. Say, in red, you're taking the correlation of the 2 modes of signal against the other 4 modes. And then that's the signature of entanglement, if it's below 1, as you crank up the power. This line here is what you have if you don't have that phonon noise. The red is the theory for the result with phonon noise and experimental data on top of it. The blue is when you take only one of the modes against all the rest. The black is when you take the two upper sidebands of the down-converted modes against all of the rest, and you see that you have even more entanglement coming out. And you can have that evolved in all other bipartitions. The pump is the weakest entangled one. You see that you have a region where you have entanglement, but then it disentangled above a certain driving power. Here you have only a pair of up and lower sideband of one of the modes. Entanglement is not as strong, but is still there. Okay? So that's basically a view that we have over the tools that you can employ using nonlinear optics and cavities to manipulate light and produce entangled fields. Entanglement and squeezing will be now the base that you are going to use for quantum information processing, for quantum information distribution in quantum machines. That will be the subject of the last theoretical class tomorrow morning. Okay? So thank you very much. Any questions? No questions? If not, coffee and picture. Roman?
Yes, group picture.
Yeah.